The integral above we were able to evaluate, but often we're going to have integrals that we can't evaluate. And so instead, I can determine whether they're convergent or divergent. And one of the ways I can do that is by comparing it to an integral that I know converges or diverges. So here I've got two functions, g of x and f of x, where f of x is less than g of x for all x in my domain. So if g of x is a convergent function as x goes to infinity, if the limit converges, the area converges. If I find a smaller area, then for sure that will also converge. The converse of this is also true. So if g of x is greater than f of x and f of x diverges, so also if f of x is divergent, then so is g of x. So let's look at an example of this. I want to determine if the integral from 3 to infinity of this function is divergent or convergent. And this is something that maybe I could evaluate with an arctan or one of those, like maybe that's a trig function. But I've just been asked if it's divergent or convergent, so I don't care what the actual value is. So what I know for sure is that this is positive, and this is also smaller than 1 over x squared. And this is for sure smaller for x greater than 3. And that's what I care about. And based on this, I know that the integral from 3 to infinity 1 over x squared dx is convergent by the p-test. Therefore, integral from 3 to infinity of 1 over x squared plus 4 dx converges by comparison. And that's all I need to say. You need to have these two parts in order to say the comparison. So stating that your function is less than the function you're comparing to, and a reason why the function you're comparing to converges.